Thanks very much. So I'll try, maybe I'll try without this, and if there's a complaint, I'll pick it up. But hopefully I can project and everyone can hear me. But let me know if you can't. I'll pick up the mic. Okay, great. So here's the title of my talk: Timelike BKL, Singularities in Chaos and AdS CFT. It's just based on a single paper. So let me explain a little bit and say I'm not, by any means an expert in the BKL sort of literature. This is the first paper I've written about the subject. Given how thorny it is, it might even be my last. So, I'm going to leave out a lot of the, basic sort of BKL stuff that several of you know better than me, and try and focus more on this part of it, the sort of AdS CFT perspective. And I'll say a few words. I'll paint sort of a cartoon of what AdS CFT is supposed to be for those of you that aren't too familiar with it. So just a little bit of basic motivation. Of course, timelike singularities seem like they would be relevant in nature. If you just look at various classical solutions of GR, they seem to appear all over the place. Now, Michales told us a little bit about how they might not be so relevant if the inner horizon is unstable and things like this. I'm not really going to comment much on that. I think you all are aware of the subtleties. But it's an important question to think about. What are timelike singularities like? Are they relevant? My motivation, again, is not going to be, potentially these things in nature. It's not even going to be a motivation in gravity. It's going to be primarily to try and interpret these objects from the point of view of quantum field theory, actually. And the map for that will be this duality here. So, okay, let's go ahead and get started. So, let's talk a little bit about AdS before we even get to BKL singularities. So this is, as many of you know, it's a maximally symmetric space of negative curvature. So the usual way we like to draw AdS is as this sort of tomato soup can. Okay, this is AdS space. And a nice coordinatization, which doesn't cover the full space, but is useful for a lot of these AdS CFT sort of calculations, is called the Poincare patch. So the metric is as follows. So it's conformal to flat space. There's just this magical factor of z squared downstairs, which actually contains a lot of the power of AdS CFT. So you can see immediately from this metric that there's a scaling isometry. If I take all the coordinates and rescale them to some number times the coordinates, the metric is invariant. Okay. So in terms of this soup can or whatever, the way I've written it, here's the conformal boundary of the space-time. So this part here is z equals 0. Z equals 0 is the conformal boundary. And in the language of AdS CFT, the statement is that you have a particular theory of quantum gravity that lives in anti-de Sitter space. That's the interior of this soup can. And it's dual, meaning any object you might want to compute in this theory of quantum gravity, you can compute by analyzing instead a dual quantum field theory that lives in one lower dimension. In particular, it lives at the boundary z equals 0. Okay, and again, I'm going to be schematic about a lot of these things. You can ask me more precise versions of it later. I'm not going to actually use the duality at the quantum level. I only care about the limit where it's classical gravity in the bulk, because I want to talk about classical notions. So we don't really need to, hurt our heads over conceptual issues in quantum gravity. So that's the basic idea. You have some, quantum gravity in here, and it's dual to some quantum field theory on the boundary of this space. Okay? Good. So what we can see immediately about this scaling isometry is that, let's say the QFT coordinates, since it lives as z equals 0, are t and xi. Okay? So what we see is that this sort of induces a scale transformation in the field theory. Okay, if you take a field theory, it's defined on the plane in the coordinates t and xi, so you just conformally rescale to ignore the z squared piece. If you just take a field theory with some coordinates t and xi and you rescale the coordinates, that's doing a scale transformation. This is the basis of trying to understand renormalization in quantum field theory. You just look at the field theory at different scales, you do your renormalization group procedure, and we see that doing the scale transformation in the field theory is related in the bulk picture to going into the interior in the bulk. So notice that z, which starts off at 0, let's say, or something very small, put some cutoff if you want, you rescale it by some number, so that takes you into the interior. So that's the simplest way to see the cartoon that renormalization group flow in the dual, I'll call it QFT, is radial evolution in the bulk. Okay, so again, some language. The bulk is the interior of the soup can, the boundary is the z equals 0 part. Okay, so there are other ways to see why this statement is true, but this is the quickest way for my purposes. Okay.
But boundary is not a part of your physical space. Boundary is boundary. I mean, in the sense of the gravity.
Well, in the sense of gravity, so the metric is fixed out here. It's a part of the physical space in that light rays can reach the boundary, so you need to put some sort of boundary conditions here. So you can think of this as a Penrose diagram, light rays go 45 degrees. So usually to make this a closed self-contained system, you just say null things are given reflecting boundary conditions, and then it's a complete system. Okay, so to get a little bit of intuition about this, let me just make a few simple statements. So in the bulk, there are two length scales. There's anti-de Sitter has a curvature scale, which I've sort of suppressed in this metric. But as I said, it has curvature. So there's the AdS length scale, and there's the Planck scale, and you could form this dimensionless ratio. And depending on what AdS CFT duality you're working with, this is related to n. And so what's n? The dual field theory is a large N gauge theory. So in the most famous example, it's a very supersymmetric Yang-Mills theory of gauge group SUN, where n is taken to infinity in the classical limit. So there's one way to relate parameters. And so then you can have, to realize this slogan over here, you can actually construct very simple solutions in the bulk that go from anti-de Sitter space of a given curvature scale to another anti-de Sitter space of a different curvature scale. So you can have a radial flow that takes you from one AdS, I'll call it AdS1, to another AdS. Maybe I'll do it like this. This just means they have different curvature scales, and we can understand and track what's happening in the dual field theory. And it has a renormalization group flow that takes you from a given n to a different n.
You're flowing to different cosmological constants, or you're flowing in the radial direction?
Yeah, the cosmological constant is often actually set by a scalar field. So it's some dynamical thing that you can give some potential and actually have it go to some other minimum.
Okay, but the flow means you're changing the cosmological constant.
Yeah, that's right. Yeah. Yes, good.
I'm sorry, so you're in AdS4 CFT 3?
I'm not going to specify. Well, once I get down to mainly the calculations I'll get to are in 4 dimensions, but so far what I'm saying is more or less general. Less than or equal to AdS7, let's say. Okay, you can have more exotic flows than this, and I think I need an eraser. Very good. So I can put, for example, within AdS, an extremal Reisner-Nordstrom black hole. This is another, solution that I can consider. And because the black hole is extremal, it actually has some enhanced scaling symmetry as you zoom into the horizon. The near horizon limit actually has an AdS2 factor. Is AdS2 cross S, however many dimensions you're in, D minus 2. And this is actually also understood not at a very precise level, but at a rough level. This is a flow from a D minus 1 dimensional CFT to a 1 dimensional CFT, or a quantum mechanical theory. So this is something that's AdS-D near the boundary, because you always fix the boundary. You always start off with AdS and D dimensions all the way out here, and then when you go into the interior, different things can happen. And if you put this big fat black hole with this near horizon limit, as you go toward the interior, you see that the metric becomes something like this. And from the rough idea that whenever you see one of these AdS spacetimes, you should imagine the field theory describing it is in one less dimension. You see that there's this kind of flow, and this is actually made more precise in some concrete settings. These compact factors you always ignore in this kind of subtracting one business. But anyway, this isn't going to be so important. I just want to give you a little bit of flavor of these RG flows, because it's going to be the basis of the things I say. Okay. Well, one more thing. If I just put a large Schwarzschild black hole, let's say. So this is some, solution of the bulk theory. This is like putting the QFT at finite temperature. So this large black hole has some, Hawking temperatures associated to it. So this is like putting the QFT at that temperature, at the temperature given by the black hole.
M squared lambda much bigger than 1 or something?
I'm sorry?
Large means M squared lambda much bigger than 1 or something?
It means the radius of curvature of the black hole, much bigger than the AdS curvature scale.
Okay.
So these are black holes which within AdS actually end up having positive specific heat. So ordinarily a Schwarzschild black hole just has negative specific heat and evaporates away. But within AdS you can make these things stable by making them very large.
So this is a Schwarzschild AdS black hole?
Yeah. Everything's always in AdS, yeah.
But we don't have AdS-CFT duality for Schwarzschild AdS black holes. Is that an assumption?
Yeah. Well, I don't know what you mean. I mean, this is one of the best understood things within AdS CFT. I mean, it depends on what you mean.
Yeah, it's just things that are asymptotically AdS that are supposed to be dual.
That's right, yeah.
It doesn't have to be AdS itself.
Right?
Yeah.
Everything is in the large N limit, so I think one has to be careful here.
Oh,
Finite
sure.
Temperature, so
Yeah.
the conjecture has been taken very far.
Yeah. Right.
Well, I mean,
all
but
these
they're
things should come with a big grain of salt.
well, there are basic things you could compute that'll show. For example, they're basic things you compute in the field theory. In the concrete examples, there are finite temperature things you could compute, which in the bulk are reproduced by things like this background and computing in this background. So, I think this much is okay.
What means this TH?
Hawking temperature. The Hawking temperature of the black hole. Yeah, that's setting the temperature of the dual theory. Okay, so now to get to the motivation after all this time, RG flow is the cornerstone of our understanding of QFT. Okay, the usual picture we have, thanks primarily to Ken Wilson, is that you have, this is supposed to be the space of field theories now. You have some point, there's some CFT that lives at this point, you deform it by some relevant operators, relevant meaning at low energies that'll have an important effect. The CFT can flow somewhere else to some, infrared CFT, and usually imagine it hits some other fixed point. So this is the UV CFT, you flow, you hit some IR CFT. This is the basic picture and cartoon we usually draw, and there are lots and lots of examples where you can realize these sorts of flows purely in field theory. But you can ask the question, I mean, these equations that give you some flow like this, there's some flow equations. Okay, these are, what's called the beta function equations. They tell you how your coupling constants flow. after you deform this CFT by some relevant operator. So again, you start off at some high energy CFT, deformed by relevant operator, you do this scale transformation to view it, on longer and longer distance scales or lower and lower energy, and you see that at some point in the very, very far infrared, it can be described by a CFT. Other things can happen too. It can become trivial. But let's just take this basic picture. And so you can ask, can this flow map have more exotic properties? For example, anytime you're faced with a map, you might want to ask, can this map be chaotic? Okay, can you start off at the CFT, and depending on small perturbations to the size of the relevant operator, can you, end up in wildly sort of different places where I'm drawing a cartoon of what chaos really is, but just to give you the idea of what you might want to ask. So you can ask this question. And in certain cases, RG flows are understood well enough that you can rule such things out. So for example, in 2D, 4D, and probably in any dimension, it's just a sort of technical abstraction. If you maintain Lorentz invariance, then you can basically rule out these kinds of more exotic features. So Lorentz invariant flows means, okay, if you're at a CFT, of course you have Lorentz invariance plus additional symmetries, scaling, and special conformal transformations. But what I mean by Lorentz invariant flows, I mean this operator that you deform your CFT by, that had better not break Lorentz invariance. So the theory along, this flow here is always Lorentz invariant along everywhere here. But you could imagine doing more exotic things. When people in, for example, condensed matter physics do more exotic things, you can deform by relevant operators which break Lorentz symmetry. Okay? And then there's no such statement. Okay? So you can ask, what about non-Lorentz invariant flows? Okay, so let's move to that. Now, okay, that's sort of the field theory motivation. I'll move now to gravity and this Timelike BKL business. So in case people don't see where I'm going, the idea, the basic idea is, okay, maybe you start off with some asymptotically AdS spacetime, you flow toward the interior, there's some, Timelike BKL kind of singularity, and very naively what this would imply is as you flow toward the interior, the evolution is chaotic. So now this is some radial flow instead of the usual time flow that we're used to. And this radial flow would be chaotic. And like I said before, the radial flow, this was a z coordinate. That thing is dual to renormalization group flow. So that seems to be a basic indication that the renormalization group flow might be chaotic if such things were allowed. Okay. A bit of a spoiler, I think the conclusion that we sort of reached in this paper is such a thing is pretty difficult to accommodate, but I'll try and paint a picture of maybe exactly why. So the basic starting point is, you take the sort of time-like version of the Kasner metric as your sort of seed metric, and I'm not going to go through these details, just want to write down this few expressions, and you ask, can this be, sort of seed of radial BKL flow? So, we actually only found out after writing our paper that Sergey had worked this stuff out 40 years ago. But anyway, it was fun hitting our heads over it and trying to work it out ourselves. But at the basic sort of, so I just put a question mark. So at the same level of rigor that BKNL originally did the BKL analysis, you can see that that in the BKL-like metric analysis, that things aren't really changed. It seems like, well, if you have some idea of what radial evolution is like, that you can have chaotic flows for let me be specific, 3 plus 1 dimensional vacuum gravity.
Excuse me, what do you mean by chaotic flow?
You want to define chaos precisely, or what do you? I mean the same sort of thing that was showed in the original BKL paper. If you do this analysis and try and turn it on its side and see how many free functions, and if you have this kind of bouncing behavior, the same thing is true. I'll be a little bit more precise about what I mean by chaos in a second.
But he's basically just switching time and radius and the usual BKL stuff and importing all the usual results.
Yeah. It follows immediately from the BKL thing. If you just stare at the equations and stick the eyes in the appropriate places, it follows immediately. But one of the things we're more curious about is this AdS CFT duality I'm talking about. It's true in a very many number of dimensions, up to 7 bulk dimensions and 6 field theory dimensions. So we kind of wanted to generalize this to higher dimensions and also to include matter. So we didn't do matter really, in higher dimensions we did sort of roughly, but the natural formalism we thought to generalize this to higher dimensions is this cosmological billiard story of Hanot and collaborators. So we tried to adopt that story, and the basic picture there is that you do some sort of ADM decomposition, and now I'm going to do a radial sort of ADM decomposition. So you have some, and already, I'll comment on this in a second actually. You have some sort of radial ADM decomposition. Three-dimensional Ricci scalar. Okay, and in this language, and unfortunately I don't have time to derive these things. You sort of map the problem into a billiard in some hyperbolic space with some infinitely sharp potential walls. And there are two types of walls. There are curvature walls. Let's see, what do I want to say about this? Okay. Curvature walls that come from the Ricci and what are called symmetry walls. From the extrinsic curvature. And the picture that is often drawn is, okay, you map it into a billiard on hyperbolic space, which is represented by this disk, and in 3 plus 1 dimensional pure gravity, the picture that Hanot and people drew, and I guess this was done even earlier in different language by Misner. I don't actually know very well the history, but they draw this kind of billiard picture for 3 plus 1 dimensional pure gravity. So you have, 3 symmetry walls. So here are the curvature walls, these curvy ones, and here are the symmetry walls. And the chaotic billiard ball problem is a billiard in one of these simplices that kind of bounces around chaotically in here. And in the language of billiards in hyperbolic space, the precise statement that is chaotic is that this simplex has finite volume, and so this, insofar as this map to this problem is precise, then this problem is chaotic in a precise sense. But in the map, there's some stuff that goes into it. Okay, so you can take their analysis and try and do this time-like version of it. Oh, and, well, for completeness, I'll draw what they... Well, okay, this is a bit small, but they like to draw these sort of Coxeter diagrams because you could relate chaos to these Coxeter diagrams. But let's draw it to show how it differs as you go to the time-like case. So this is the ordinary space-like BKL. So we just redid the analysis in 3 plus 1 dimensional pure gravity just to see how this Iwasawa decomposition works. And there is a little bit of subtlety. So the decomposition they used required diagonalizing this metric, the 3 metric, in terms of an Iwasawa decomposition, in terms of upper triangular matrices. And you can't do that in general for a Lorentzian metric. So in their case, they had time here, and this was a pure Euclidean metric, in which case you could do it. In a general Lorentzian metric, you can't. If you have some silly metric like this, you can't really diagonalize this with upper triangular matrices. So you can expect that it might break down. And in fact, it does. So if you went through naively, what you would find is that two of these symmetry walls, which are infinitely sharp walls that the ball bounces against, seem to turn into infinite wells. They seem to attract the ball and lead it to escape out of this region and lead it to be not chaotic. But in fact, I think that's the wrong picture. That's the Iwasawa decomposition breaking down. If you work in instead a orthogonal decomposition, which just means diagonalize this, this symmetric matrix by orthogonal matrices, you see that the picture is actually very similar. So you have two of your symmetry walls, these guys, which look like they're becoming wells, they actually become transparent. Okay? So the billiard ends up being something like this, so then you have a bigger sort of billiard region that you could bounce around in, and this is still chaotic, and the Coxeter diagram is slightly different. It's this. So even in, let's say, Iwasawa or orthogonal decomposition, chaos remains. Okay, so these two pictures agree with each other. There was a paper written that in the Iwasawa decomposition actually seems like you lose chaos, but I think the basic mistake was that they were faced with this, what's effectively a coordinate singularity in the Iwasawa decomposition. I think it's just the analog of working in Schwarzschild coordinates and seeing that something is blowing up near the horizon, whereas you can work in Creswell coordinates and be fine. So it's nice that the two various ways of looking at it agree. How much time do I have?
You can still 5 minutes.
5 minutes? Okay. Okay, good. Okay, but then you can ask, I'm asking about flowing toward a naked singularity within AdS. This is kind of a weird thing. You can ask, are naked singularities allowed in AdS CFT? And here we still don't have a complete set of rules, but there's some basic things you can say. For example, negative mass Schwarzschild is something with a naked time-like singularity. Okay, this should not be allowed in AdS CFT because insofar as the dual CFT is unitary with some, zero energy ground state, the negative mass AdS Schwarzschild geometry would map to a negative energy state in the field theory, and that would cause the field theory to be sick. So there are basic things like that where you have access to the full geometry, you can compute the asymptotic charges, you can see if something is sensible. But we couldn't really do that in this case because we weren't able to construct, obviously, flows from an asymptotically AdS geometry to some time-like kind of BKL singularity. But you can ask some sort of basic effective questions, like some basic physical criterion is that if you have 2 points, I'm going to not be able to draw this at all. If you have 2 points on the boundary that are space-like separated, then they had better not be time-like or null separated by going through the bulk. Okay, that would imply some sort of acausality in the field theory, because you take 2 points, the boundary field theory is on just some flat metric. If they're space-like separated, you better not be able to send a signal through the bulk that reaches the other point, with some time-like or null separation. So causality preservation is important. And if you look at the, again, negative mass Schwarzschild geometry, that violates this criterion. So you can get time advance by going toward the time-like singularity and violate causality in the field theory. So that's another way to rule out that geometry. And so it turns out that you need, in terms of these Kasner exponents, to preserve causality, you need that the Kasner exponent in the time direction is greater than all the Kasner exponents in the spatial direction, so that you don't have any problems with causality. Now this is an effective description, but I think the basic idea is correct. Even in some full thing you might construct, this is true. And of course, when you're bouncing through different geometries, you're going to be faced with pt less than pxi at some point generically. So this seems to be a kind of strong constraint on having this type of singularity, and again is one of the reasons why I said that it seems like this kind of picture that we were trying to paint might be very strongly constrained if it exists at all. Okay, that's the meat of what I wanted to say. A few more things is, even in AdS CFT, we don't expect at the end of the day for there to be some naked singularity living inside. There's some few very basic singularities that we've understood, how their resolution works. These type of singularities, naked time-like curvature singularities, we don't understand at all. But insofar as they're resolved, there's some ultimate, infrared that we don't quite understand. But what seems to imply is that this chaotic behavior I was talking about in the RG flow may only be a transient effect. You may, if you have some controlled approximation such that you're BKL-like in some region here before you have to bring in the higher curvature, the stringy and quantum corrections. If you're BKL-like in some region here, then it'll be chaotic for a while, and then depending on how the resolution of the singularity works, maybe you'll still hit a fixed point, or maybe it'll continue to be chaotic. I don't know, that sounds a little weird. But it's just unknown what happens if you were to have the full resolved geometry at the stringier quantum level. And a few more things. When you go to higher dimensions using this same sort of picture, then you do seem to get physical wells, actually, because then the analytic continuation, or even just analyzing it directly with this sort of decomposition, shows you that it was actually very special in 3+1 dimensions that these curvature walls all remained walls, and when you go up even one more dimension, you start picking up curvature wells, which do not seem like artifacts of any sort of decomposition. This part we didn't analyze so carefully, but it seems to indicate that you lose chaos in higher than 3+1 dimensions. Also, this analysis, we didn't look at very many types of matter, but it looked like as soon as you include matter, you also lose chaos. So this is more reasons why I'm saying this is very restrictive, this picture of a singularity in the interior of AdS. 3+1 dimensional pure gravity seems kind of special, but in AdS CFT land, 3+1 dimensional pure gravity is not expected to be dual to any sort of field theory. You really need the full supergravity, which has matter fields and things like that. And that guy does not seem to be well behaved. Well, it doesn't seem to be chaotic in this way. Okay, at this point I'm just sort of listing results. The one promising feature was that there were chaotic field theory flows that were constructed in the context of AdS CFT, which were very similar in mathematical structure to these guys. They reduced the language to the same language in this billiard problem of, wild reflections in these chambers and blah, blah, blah. So, maybe there's some connection to be made at the end of the day there. But, okay, that's basically the set of results. I want to just say a few things about future directions. It's okay, I can eat into my question time. I mentioned matter, I mentioned higher dimensions. Okay, of course you would want to try and actually embed one of these guys in AdS CFT. That would be, or just in AdS, that would be great to get a handle on what is or is not physically allowed. Of course, all this analysis is at a heuristic level. This is not, I don't know, the precise gauge invariant or algebraic or however you want to analyze this in the most precise way. This is not that. This is sort of a maybe old school BKL. But the dream, which is originally why I was thinking about this, is, okay, AdS CFT in the examples that we have is, for certain questions, fairly well understood. There's a different kind of duality, I'm not going to go into explaining it, which is way less understood. There's only a single example, which doesn't even seem to be complete, called DSCF, and this is trying to describe de Sitter space, so cosmologies that we care about. So here's the Penrose diagram of de Sitter, and here's the flat slicing, let's say. And so in this picture, of course, you can be faced, well, this is probably not the picture we want. We probably want something that starts off with something like this and becomes asymptotically de Sitter. Here now you can be faced with the ordinary space-like BKL type singularities. So if we had control over an example of this nature, then we could actually try and embed these singularities there. And there's reason to expect that the dual field theory would be much more likely to accommodate this kind of singularity. Because in this duality, the dual field theory is not unitary. Okay? In AdS CFT, the dual field theory is unitary. And once you have non-unitary field theories, this kind of flow is actually not very weird. We've seen very weird sorts of renormalization group flows in non-unitary field theories, which, okay, they aren't exactly chaotic, but they're very close to chaotic. And so the restrictions on this kind of thing are much milder. So that is, I don't know, a dream for 50, 60 years from now or something like that. But I think that's all I wanted to say. Thank you for your attention.
Questions?
I'm slightly confused with the philosophy because we would expect that if there was such a bulk space-time, and we are having a timelike singularity, and there is a BKL phenomena that it is occurring in the strong field limit of gravity in the bulk. But the AdS-CFT duality also teaches us that duality is between the strong field and the weak field in CFT. So why would you expect a chaos in the IR regime of CFT?
Sorry. I mean right. So what you do is you set. So you have these parameters in the bulk: L AdS, L Planck, and L string. Okay, and you can set the ratios L AdS. So you set these ratios L AdS over L Planck and L AdS over L string. Okay, and these things specify your dual field theory. So this thing specifies n, and this thing, once and for all, specifies the coupling constant. Okay, so so this thing could be strong or weak. And then what the flow does, this field theory at either strong or weak coupling, I mean, it's going to be strong coupling because I'm starting with classical gravity, at the asymptotics. There's going to be some strongly coupled thing, and then the flow that it has, independent of whether gravity becomes strong in the sense of the curvature invariance becoming large, whatever that does is contained within this field theory of strong coupling. I mean, this guy will flow. Presumably, it'll flow to weak coupling, as you say. Maybe something like that is happening. But if you could track the RG flow of this strongly coupled theory, it should be contained in that object.
Yeah, but the point is that lambda is going to the IR limit in this flow.
Yeah.
Then you are approaching the BKL behavior in the bulk.
Yes.
So my confusion is that the BKL is essentially a strong field phenomenon in gravity, the chaos essentially.
Yes.
Why do we expect the chaos in the dual theory to be a weak regime, IR regime phenomenon?
I don't think we have any expectation of what it is in dual field theory. We don't really have any precise examples of chaotic renormalization group flows. So
Exactly.
I see. Yeah, there's no expectation. The idea here is to try and build up some sort of expectation.
Maybe you already said this earlier and I came in a bit late actually, but why is this question important? That is, are naked singularities allowed in?
It's important because there are some naked singularities which are manifestly not allowed. So the example that I mentioned is negative mass Schwarzschild has a naked singularity, and something like that is not allowed. And the basic criterion that you can use to try and rule these out, other than looking at the charges, like in the case of negative mass Schwarzschild, is make sure the dual field theory remains causal. There's some geometries you could insert where you would lose causality in the field theory. And this seems to be a strong constraint on radial BKL type flows. Yeah.
I have a remark. If you consider the oscillated singularity, there is a mixing of the Kastner indices. But if you consider the generalized special anisotropic singularity, something like Lifshitz-Khalatnikov type, and consider this inequality, so you deal with so-called paradox-like singularity, which is very, very unusual. I am sure this is a completely new type of singularity, and there is a lot of delicate detail. For example, consider this causality of the space-time, because if you consider the distance between 2 points, in this case the minimal distance is not so obvious. The minimal distance you have go to the singularity, then along singularity, and to the another point. So.
Okay, yeah. In the AdS-CFT context, I never want to go to the singularity, so that I'm just not going to think about.
No, if you consider this is the space, is the distance space-like or time-like, you have this.
So usually there are supposed to be various entries in the AdS-CFT dictionary, right? So we're told that, well, okay, black holes on the AdS side are supposed to be thermal states on the CFT side. And formation of a black hole means that the field theory thermalizes. So you're allowed to, build in time-like singularities to the bulk, and you really would be building them in. They don't dynamically arise, despite the idea of trying to treat R as a dynamical variable, which really doesn't, 3R as a time, which really doesn't work mathematically. But you're allowed to build these things in. But if you do build them into the bulk, what is the entry in the dictionary? That is, what does a time-like singularity at the bulk correspond to in the CFT side?
Yeah, there's no entry. I was operating from the point of view, at the very basic level, any classical geometry you have in the bulk, and I'll consider this a classical geometry where I exercise some region around the singularity, and this region is defined by where, let's say, stringy and quantum corrections become important. Then if this is really some sort of classical geometry, then this is some state, roughly speaking, in the bulk Hilbert space. This should be dual to some state in the dual field theory. Beyond that, and this picture of RG flow as you go toward the interior, there's no statement like the one for black holes of a naked singularity would be something like this. We're trying to paint a sort of picture of that in the case of a BKL type naked singularity of saying, this seems to be dual to kind of chaotic sort of flow as you go toward the interior. But beyond that, there's no understanding. The very little work that's been done in understanding naked singularities in AdS CFT is whether they're allowed by some general rules like causality.
Yeah, although there it sounds like you have a sort of reductio ad absurdum, because you said that you need the sort of timepiece to have Kasner exponent that's within a certain range.
Yeah.
But the usual BKL chaos will preclude that.
I agree.
So it almost sounds like the sort of punchline we should take away is that that the chaotic type singularities are not allowed to be.
Yeah. That's what I was saying, that this is very strongly constrained in AdS CFT. If I had to bet money, I would bet that this doesn't exist once we're able to understand everything. But the analysis at this level is a bit heuristic, and people smarter than me can do something very precise and get a better handle on this sort of thing. Because this is just sticking to a specific radial Kasner solution. Now, I don't know too much about the details of when you actually bounce, how much time you spend in the different sorts of regions and what it looks like. So maybe there's some averaging out that could occur. Again, I bet not, because this is a large range of the exponents. But there's a tiny sliver, just to hedge a little bit, that something like this may be true in some very controlled kind of situation. But yeah, I agree with you. I expect not.
Questions?